Good afternoon, everybody.
Good afternoon.
So this question for only participants, sir. So how many you know about ocean waves? So, my dear friends, today we are going to discuss on ocean waves and the techniques behind ocean activities and wave properties and the physical principles. And generally, you know that wave is a disturbance of kind of disturbance which is coming from the, propagating in the form of wave. Uh, Generally, it breaks on shore or a rock or a boat at the sea. But there are so many types of waves. As you know that internal waves, tsunami waves, all these things are. Let's welcome Professor Prasad K. Bhaskaran, sir. He's an expert in ocean wave modeling and ocean wave engineering, who is currently working as a professor and former head of the Department of Oceaneering Engineering at IIT Kharagpur. He did his master's in oceanography from Andhra University, and he got PhD in atmospheric and oceanic sciences from University. Later, he joined as a project scientist and worked for 2.5 years on a topic of development of operational forecasting model for the Indian seas. Later, he worked as a physical oceanographer at the University of Petroleum Minerals Kingdom of Saudi Arabia and the United Nations Compensation Commission project to assess the impact of oil spill during 1991 on the Gulf waters. He also worked as a project scientist at Inquiries, Hyderabad, and as a postdoctoral researcher by Naval Research Laboratory at Louisiana State University, USA, about 4 years. And then later he joined as assistant at IIT Kharagpur in 2004. His basic interest is the development of the model physics and parameterizations for source and sink mechanism in ocean wave models, with practical relevance in ocean engineering problems. As you know that he's a very good expert in ocean wave modeling, coupled wave hydrodynamic models, coastal engineering, marine acoustics, wind wave climate studies, and topical studies on AC interaction dynamics, with special reference to Indian Ocean. Some of his unique contributions are he included parameterization of rain-induced surface roughness and its implementation in third generation models. And he is also a lead member in the preparation of this tsunami travel time. He did significant contributions on application of soft computing techniques for retrieval of oceanographic parameters, especially with the Argo data, mixed layer depth, and barrier layer thickness for the Indian Ocean region. He guided 12 PhD students and 2 postdoctoral research scholars. He published 205 research articles in peer-reviewed national and international journals, and 5 more PhD students are still with him. And he is a recipient of the James Rennell Fellow awarded by the Ministry of Earth Sciences, Government of India. And he is also a member of the Board of Studies of Cochin University, Andhra University, QFOS Cochin. And he is also a national expert member in the Central Water Commission, Ministry of Water Resources, expert panel member, expert panel member in ocean engineering. He is also a member in the Prime Minister Research Fellows expert panel, and a panel member in the Naval Research Board, the DRDO, and is also a committee member, advisor program for the Advisor and Monitoring Committee for National Network Program on Climate Change and Coastal Vulnerability Department of Science and Technology, and is an advisor committee for Ranbir and Chitta School of Infrastructure Design and Management, IIT Kharagpur. A lot of things are there. He's a project coordinator for the Center for Excellence in Climate Change at IIT Kharagpur, sponsored by the DST. He is also 4 patents, copyrights on his credits. So, my dear friends, today he is going to give us a lecture on basics of the ocean wave modeling and its application for the Indian seas. Let us welcome Prasad sir to give his presentation. Thank you.
Yeah. Thank you, Professor Sunita, for the introduction. So good afternoon to all the participants. It is my pleasure actually to give a talk for this national webinar series. And I'm very happy that Professor Sunita has taken up this very good initiative in arranging the webinar series. It's really useful, and extremely I'm very happy that the students will be much benefited from the people actually who are actually expert in different areas. Yes, in 1989 to 1991, I was a student of Andhra University. I've done my master's MSc degree in marine sciences with a specialization in physical oceanography. So in today, I will be talking about the basics in ocean wave modeling. So let me share my presentation. It is saying the presentation is visible?
Yes, sir. Yes. Yeah.
Okay. So the topic will be on basics of ocean wave modeling and its application for the Indian seas. So this is the outline of my presentation today. I'll be talking about starting with the basics, the basic characteristics of ocean waves. Then I will be dealing with the wave energy spectrum, why the wave energy spectrum is important and how it is relevant in understanding the characteristics of ocean waves. Further, I will be talking about the numerical modeling. How do we model these ocean waves? How do we incorporate the model spectra, the different types of model classes, the formulation of the wave energy balance, and the state-of-art wave models we have at present today. Thereafter, I will be converging my discussion on SWAN. SWAN is basically a shallow water wave model. So I'll be giving more emphasis on shallow water wave model. Of course, I'll be talking about the other wave models also. Finally, I'll be touching on the role of satellites, how the satellites are important in ocean wave research. And I'll conclude my presentation by giving some questions to the young researchers. Because ocean waves is a very, very important topic. It is understood that it is a important topic for the air-sea interaction studies, and it is very important in disaster management, because today you are finding a lot of coastal flooding from tropical cyclones, extreme waves. These are happening very frequently, and we can actually give a solution to this problem. Of course, the solution basically is an engineering solution, but the forecasting of these waves can be done. And today I'll be touching about how we can forecast these waves. So I'll be first starting about the basic characteristics of ocean waves. Now let me tell about what type of waves I'm talking about. We have actually different types of wave systems in the ocean, different types of wave systems. So this figure, the top figure, actually gives an idea of the different waves that we have in the ocean, starting with capillary waves, the smallest waves that you can find on the ocean surface. And this also can be generated in a tank. Suppose you have a bucket of water and you give an external disturbance, you find the capillary waves which are generated. And of course, the capillary waves have got very low energy, so it doesn't make it is not a threat in terms, but it starts with the capillary waves. And the capillary waves again gets converted in the higher order form as the gravity capillary waves. These are called as the ultra gravity waves. Then you have the surface gravity waves, which are coming in this time period. It starts from 1 second and goes up to 30 seconds. Then beyond 30 seconds, you have got a different type of wave system, which is called as infragravity waves. Infragravity waves, and you can see that the time period can go from 30 seconds, it can go up to about few minutes, 5 minutes. Then you have another type of wave system called the tsunamis, and all basically comes in this time scale actually, like it comes around 10 to 11 minutes. If you see the tsunami wave basically comes in the time period of few minutes, that is from 10 to 11 minutes. Because after the 2004 tsunami that happened, that has triggered tsunami in the Indian Ocean, the first wave actually has come and the second wave almost followed after 10 to 11 minutes. So that is a typical time period that you have. But you have another type of wave system which is longer than that, that is called the tidal waves. You have storm surges, tsunamis, sieges all coming in this particular time frame. Then the astronomical bodies, the gravitational force due to astronomical bodies can create a different type of wave system, which are popularly called as the tidal waves. You have got a time period from 12 hours to 24 hours. And beyond this also you have got planetary waves, like you have the Rossby waves, Kelvin waves, Yana waves, different types of wave systems. So this figure, the top figure, basically gives you an idea of the different type of wave systems that can exist in the ocean. The different types of wave systems that can exist in the ocean. Now today's talk will be focusing on this particular band, which is ordinary gravity waves. The time period starts somewhere from 2 seconds, it can go up to around 30 seconds. And these waves are created by the wind actually that is blowing on the water surface. The wind that is blowing on the water surface can create the surface gravity waves. And these waves are actually visible. Suppose you are sailing in a ship, you can see that the surface of the ocean, basically the undulations that you find on the ocean surface, these are basically the surface gravity waves. So the sketch, the below sketch actually gives a very simplified version of a wave. As what you see from this figure, we can see a crest that is followed by a trough. Again, you find a crest, again that is followed by a trough. So the basic wave characteristics that you find from this figure is the height of the wave. When you say wave height is the vertical distance between the crest to the trough. That means the distance from the crest going up to the trough. This is basically double the amplitude. So this solid line, what you find here is the mean sea level. So you have the amplitude which is contributed by the crest and the amplitude which is contributed by the trough, and double of that gives you the wave height. Similarly, you can find out the wave period. The number of waves that is crossing a particular location gives you the indication of the wave period, and the direction in which the waves are moving gives you the indication of the wave direction. So to understand the ocean waves, there are three important parameters. One is called the wave height, one is the wave period, and the wave direction. these three quantities gives you the information about the waves. So to model the waves, you should have an idea about how we can get these three parameters. So I will be talking about the basics of modeling after some time. But before I go into that, I would like to introduce some very important parameters which are needed to be understood fully. So yes, this particular slide gives the contributions that has taken place from 1940s till present. So if you see this table, we can find that statistical theory actually started along with the nonlinear theory, and there has been a lot of studies that has been done in the 1940s. But before 1940s also there are a lot of studies which have been done primarily by mathematicians. In context of the ocean waves, there is a theory which was given in the year of 1847. That is by Stokes actually. So it's a very popular theory. I will talk about that when I come later. But to give an idea about the different types of advancements that has been made, it started in the 1940s with the theory of random noise. Then in 1950, different name for that. The real ocean waves are actually random waves, random chaotic waves. They do not have the shape of a sine wave. The reason is when you have the wind which is blowing, of course I will talk about, when I talk about the wave growth, I think you can understand actually how the different wave shapes are actually created or how the different wavelets are created. Now these are the two theories which were very important from the past, and of course still the development of theories is an ongoing task. There are a lot of work which has been done on the theoretical developments, and theoretical developments takes more time. So you can see that when the wave models are improving with time, there are a lot of new additions that has been added to the wave models. In addition to these theoretical studies, there also has been a lot of experimental studies, experimental and field measurements that have been conducted to understand the characteristics of ocean waves. So there has been a lot of development on the ocean instrumentation. Like to understand the ocean waves, the most popular instrument that is being used is called as the wave rider buoy. The wave rider buoy is an instrument which can measure the wave spectrum, and from the wave spectrum you can derive the parameters like the wave height, wave period, wave direction for both long waves as well as short waves. Both you can derive. So the development of instrumentation is also parallelly going on. So today actually you have got very robust instruments like ocean. With the wave rider buoy is a very good instrument. It can give you the complete details of the wave profile. So these studies also started from the 1940s. There are some basic studies which are conducted, and from 1980s onwards, you can find there has been a revolution in the ocean observing systems, and that basically happened due to satellites, the remote sensing techniques. Today, the remote sensing techniques actually are very, very important to understand the wave climate. I'll be giving more details of that when I go into the next slides. So remote sensing is also an area. The satellite observations of the ocean surface is gaining popularity, and a lot of studies are also being done in this direction. In waves, one should understand how the spectrum basically evolves, the evolution of the wave spectrum. Now, the evolution of the wave spectrum is a nonlinear process. I'll be talking about that actually after some time, how the wave spectrum basically dynamically changes with time. So one of the popular experiments was called the John Swaff. This was done in the year 1973. The John Swaff basically stands for the Joint North Sea Wave Project. It was a field campaign experiment done in the North Atlantic to develop a spectrum which can be used for wave models. And today, the state-of-art wave models uses the John Swaff spectrum because it is a superior spectrum as compared to the spectrum that has been developed in 1950s. Because in 1950s also there was a spectrum that was developed. It was called the Phillips spectrum. And of course, there was some limitations with the Phillips spectrum. It was corrected in 1964 by Pearson and Moskowitz. They have developed a spectrum for the fully developed sea. And that spectrum also had a limitation, and that was taken care in the John Swaff. That is in 1973. They have developed a spectrum which can be used both for deep water and shallow water. So the state-of-art wave models what we have today uses the John Swaff spectrum. I'll be talking in detail about the John Swaff after some time. In 1980s, there has been a very good studies on the Japan Sea that is being using the Hexos platform and the SWAD and the RASX, which were basically to understand the AIDS interaction parameterization. One of the challenging problems in AIDS interaction is what is the momentum transfer, or how does the momentum transfer takes place between the atmosphere to the oceans, or how much of energy is basically imparted in generation of waves, and what is the amount of energy that is imparted in the generation of currents. Because when a wind is blowing on the water surface, it can do two things. One is it can generate waves, it can also generate currents. A part of energy goes in generation of waves, and the remaining part goes in the generation of currents. So there has been very significant experiments that has been conducted to understand this process. So these are the names of those experiments, like HEXOS, SWAD, and RASX. And in 2000s, the importance of coupled atmosphere and ocean models. So that was the era actually. In the earlier days, that is before 2000s, the wave models have been studied independently. Independently means this was a standalone model. The model can be used only for understanding the waves. But as I showed in the previous figure, the atmosphere, ocean, it is a part of the Earth system. It is all coupled. So the importance of the coupling the various components of the Earth system has been brought out. And the coupled models are very popular today. So today you have got a wave and hydrodynamic model that is coupled. But of course, I'm not going to discuss on that in the today's talk, because that forms a different topic, and there are a lot of studies which have been done on that also. So the coupled models are the most popular models that is being used today to understand actually the coastal processes and also the extreme water levels during tropical cyclones and extreme waves. And the fifth point, what we see here, is called the wave forecasting techniques. Now, the wave forecasting techniques became very popular after the World War II. After the World War II, the US Navy actually has called upon some of the eminent scientists working in this area. So, as what we see here in 1950, if you see this table, I have mentioned the names SMB. SMB stands for Swerdrup, Munk, Britsneser. Swerdrup, Munk, and Britsneser jointly has developed a nomogram. I'll be showing you the nomogram after some time. How does it look like, and what is the information that we can get from a nomogram? So there were two popular nomograms which were developed. One was by SMB. The other formulation was given by PNJ. It stands for Pearson, Newman, James. Pearson, Newman, and James. So Swerdrup, Munk, Britsneser, Pearson, Newman, James, they have developed semi-empirical formulas, and this knowledge was translated into nomograms, which can be used to understand the wave characteristics. If you know what is the wind speed, what's the duration, what is the fetch. If these parameters are known, you can pick out from the nomogram what could be the possible wave height. This is how it started in the 1950s. Now, these nomograms eventually had a lot of limitations, and it failed. Why I'm showing this table is the people, the students, the young students and the researchers, they should have an idea what happened in the past and how the things have come till today. So this knowledge should be there. So that is the reason why I'm showing this slide. So how the things started in the past. So that is what I'm talking about. The Swerdrup, Munk, and Britsneser, Pearson, Newman, James, they developed nomograms. The nomograms had a limitation, and after that the nomograms is used no more. But in the mid of 1960s, or you can say early 1970s, there has been a lot of effort to forecast the ocean waves. So by that time it was well understood that the nomograms cannot be used. So the approach was completely different. So in 1950s, there was actually a mathematician who developed a formulation called as the energy balance equation. I'll be showing that after some time. Now the energy balance equation could be used to understand the spatial and temporal variation of ocean waves. That means if you know actually how the energy is varying as a function of space and time, you can forecast the ocean waves. Of course, that requires a lot of physical parameterizations. I'll be talking about that after some time, how the parameterizations have been made and how it can be used for wave forecasting. Now, once the energy balance concept has been conceived, there has been a lot of interest that has been generated by people from Europe, US, and different parts of the world. And they come out with a second generation wave model. A second generation wave model. So the first generation wave models are basically the nomograms. That is what I just now said. Nomograms had some limitation, And second generation wave models try to give a better idea or a better representation of the ocean waves. Now, second generation wave models also had a limitation. So that was realized in the 1980s, or you can say in the it started in 1980s actually. 1980s, people understood actually that these second generation wave models are also not effective. They had some very serious limitations. I'll be talking about what are the limitations after some time. The third generation models have come into use. So today the models what we use, today the state of art wave models what we have is called as the third generation wave models. So the third generation wave models are very robust. The prediction skill is very good. And you can see that in India you have an agency called INCOIS, Indian National Center for Ocean Information Service, which is under the Ministry of Earth Sciences and located in Hyderabad. So if you go to the website of INCOIS, you can see that there are so many products. One of the product is Ocean State Forecast. So in Ocean State Forecast, if you click on that link, you can see that the wave predictions are being done. So these wave predictions are basically done using the third generation wave models. So today's presentation, I will be talking about the third generation wave model because, of course, these are all historical things, but the one that we are using today is the third generation wave model. And some of the latest additions what we have in this third generation wave model is the ensemble data assimilation techniques. So that is the latest one that is being carried forward. And so like this, the what you can say, the field is basically growing. So this table gives you a complete idea of what are the studies that have been done in the past and what is being carried out today. Now, before I go into the details, I will try to give some general idea about some of the classical works that has been done or that has been carried out in India. So before I go into the Indian conditions, let me talk a little bit about the international scenario. What were the developments that has been done? Some of the classical studies on wave models started with the small amplitude wave theory. The small amplitude wave theory. It is also called as the iris wave theory. It is very popularly in the textbooks and all you can find. It is referred as iris wave theory. It is also called as small amplitude wave theory. Now the small amplitude wave theory is also referred as linear wave theory. It is called the linear wave theory. Now to understand this theory, there has been basic assumptions that has been used. That is, the fluid is incompressible, the fluid is irrotational, and the fluid is inviscid. The fluid is incompressible. Yes, it is incompressible because we are dealing with the surface gravity waves. We are not dealing with the processes that is happening below the ocean. So the condition of incompressible is valid because we are talking at the surface. Now, the other two conditions are inviscid and the irrotational. That is the water particle motion. Using these basic assumptions, you can with appropriate boundary conditions like the free surface kinematic boundary condition, the bottom boundary conditions, etc., we can define a parameter called as the velocity potential. Now, the solution of this velocity potential, from the solution of the velocity potential, we can come out with a relation as what we see here. This is called as the dispersion relation. This is one of the very important contributions which has come out from the small amplitude wave theory or the linear wave theory. Now, as we see from this equation, the left-hand side of the equation is a term called omega. Omega basically is called the angular frequency. So if you expand omega, you can write omega as 2 pi multiplied by frequency. That is 2 pi f. And of course, frequency you can write as reciprocal of time period. Or you can write 2 pi divided by t. So I can replace omega as 2 pi by t, the square of that. G stands for gravity. K stands for the wave number. That is 2 pi divided by lambda. And you have got a hyperbolic function here. It's a tan hyperbolic function. The function of k into h. Of course, this tan hyperbolic mathematically you can expand by using the exponential function. Suppose we want to expand tan hyperbolic x. You can write tan hyperbolic x as e to the power of x plus e to the power of minus x divided by e to the power of x minus e to the power of minus x. X can be replaced with k into h. K is the wave number. So wave number is 2 pi by lambda. H is the water depth. So this small h basically represents the water depth. So you are multiplying the wave number with water depth. Suppose we take the water depth is very large. If suppose H is very large, H is very large means the water depth is very large. That means deep water. In that case, what happens? In that case, your exponential function reduces to 1. The tan hyperbolic function becomes equal to 1. Then your equation simplifies and becomes omega squared is equal to gk. And omega by definition is angular frequency, that is 2 pi by t. K is the wave number, that is 2 pi by lambda. So if you try to connect both of that, you get a relation called L is equal to, L is nothing but lambda, that is wavelength, 1.56 times t. T is the time period. So if you know what is the time period of the wave, you can find out what is the wavelength. So in the first figure that I have shown, I was talking about the surface gravity waves, which has got a time period starting from 2 seconds going up to 30 seconds. Suppose we take 2 seconds. So your t is equal to 2 seconds. So t square becomes 4 and L will become 1.56 multiplied by 4, which is approximately 6 meters. Yeah, close to 6 meters. Suppose you take t is equal to 30 seconds, t square is 900 multiplied by 1.5, it approximately becomes 1.3 kilometers. So when a wind is blowing on the ocean surface, it can generate waves having a wavelength of 6 meters going up to 1.3 kilometers. Now, when all these things are mixed up, you can see that the sea surface is completely, it is not a simple sine wave. It is a chaotic wave, random wave. That is what we are trying to model. So this contribution of the linear wave theory is very, very important. So it gives an important relation connecting the wavelength lambda with the time period t. Now same equation, if I use the same equation and if I say in shallow water H is very small. H is very small. So your tan hyperbolic function approximately becomes equivalent to kh. So this equation reduces to omega squared is equal to gk multiplied by kh. That is what I have written here, gk multiplied by kh. And if you try to connect these two equations, we can get the speed of the wave. That is, this is nothing but your lambda by t. That is equivalent to square root of g multiplied by h. G is the gravity, h is the water depth. So the square root of g into h is the speed in which a long wave moves in the shallow water. For example, in the previous slide, I was talking about a tsunami wave. A tsunami wave is a long wave. So I can use this equation to find out what is the speed of the tsunami wave. So in this equation, if you know what is the water depth, of course, gravity is constant. So you can find out what is the speed of the wave. And you can see that the speed of the wave reduces when it comes from the deeper ocean towards the shallow water. This is one of the biggest contributions that has come out from the linear wave theory. Now, the linear wave theory also has got a limitation. This theory is good because it gives you a very simplified formula. Of course, the formula actually has got a limitation. That's what I was saying. The linear wave theory can be used if your wave profile is sinusoidal. But very rarely that you find your wave profile is sinusoidal. Sinusoidal wave profile may be possible in the deep water. But when it comes to the shallow water, your sinusoidal wave profile is no longer valid. So what happens to the waves in shallow water? I'll show you a figure after some time. The shape of the wave does not look like a sine wave. Your wavelength is very large. Your wave amplitude is very small. That means your wave height is very small and your lambda is very long. So the shape of the wave is not a sinusoidal wave. For such type of waves, there has been higher order wave theories called as the Stokes formula. Now Stokes formula has been very popularly used actually, and it has been used for a very long time. And Stokes waves are actually valid actually for the coastal waters as well as in the nearshore waters. Now you see this figure. This figure actually shows how the water particle velocity moves on a wave. So what we see here is the wave profile, and on the wave profile you can see how the water particle motion, how the water particle is moving. You can see this. So basically why I put this figure is to give you an understanding. Actually, if you want to understand whether the water is moving, the water is not moving. It is basically the profile that you're finding. It is an illusion that you find. To make it more clear, you can do this in a small, you can do an experiment using a small bucket. In a bucket of water, if you give a disturbance, what you find is you find the capillary waves which are generated, and slowly these capillary waves moves away from the source region. It reaches the rim of the bucket. The same thing that you can apply in the huge ocean also. In the ocean, what happens? The waves are triggered or the waves are generated in the deep ocean. The energy basically moves, and when it comes to the shallow water, the energy basically gets dissipated because of many physical processes. I'll talk about that when I go into more details about the shallow water waves. So this figure basically shows how the water particle, orbital motion of the water particles when you go along the wave, you can see that it basically is like a circular orbit. And this orbit basically, you can see here, this particular orbit basically gets transformed into this because the profile is basically changing. So you can use a circular profile for the water particle motion in a sinusoidal wave for the deep ocean, and the diameter of these particles basically reduces when as a function of water depth. So this basically shows the surface profile, but when you go down, what happens is the diameter of the circles reduces. I'll show that in the next slide. But if you see this equation that I've given, this equation is basically the solution of the wave equation. So in this equation, it's a functional dependence of two parameters, x and t. So if I take the time t is equal to 0, that means I'm taking the time t is equal to 0, then what happens is the equation becomes zeta of x is equal to a sine kx. This is very much similar to the wave motion that is recorded by a wave rider buoy, because in a wave rider buoy, which is an instrument that is measuring the waves, it is already, the position is fixed. That means your x is fixed. So when your x is fixed, basically it becomes zeta of t is equal to a sine minus omega t. It basically gives the oscillatory motion of the wave profile. Now there is another important thing. The circular motion that I have just now talked. After some time, what happens is the circular motion keeps on repeating, and after a long period of time, you find there is a horizontal motion that is seen, which is very popularly called as the Stokes drift. Now, Stokes drift basically talks about actually how the particle basically moves for a long period of time. This is again given by Stokes actually. Now, this is what I was talking about. The circular motion basically reduces, and after a particular time, it vanishes. So basically what I mean to say here is, in the deep ocean, the water depth actually has nothing to do with, the water depth has no role. The waves are free to travel in any direction. It can travel 360 degrees. If the wind is changing, the wave direction can also change. But that is not the case when the waves comes to shallow water. The moment it comes to shallow water, it basically obeys the Snell's law in physics. The Snell's law in physics is a very popular law. In optics, I think all of us have studied that. When a light ray is traveling from a rarer medium to a denser medium, it bends towards the normal. The same concept can be applied for the ocean waves also. So for the ocean waves, the deep water is the rarer medium and the shallow water is the denser medium. So it obeys the Snell's law, so you can have wave refraction. So what happens during wave refraction is the direction of the wave basically changes. Now, one of the important concept in the linear wave theory is the Arcel's number. Arcel's number basically describes what is the limitation of the linear wave theory. So Arcel's number is a very popular number in fluid dynamics. It talks about the nonlinearity of the long surface gravity waves. Of course, it is a non-dimensional parameter, and it was formulated in the year 1953 actually. Yes, it is 1953 by a person called as Fritz Arcel. He is a very popular, he's a mathematician and very well-known fluid mechanics. He has done a lot of studies on fluid mechanics. So Arcel has basically given a relation from the Stokes wave expansion. What happens is when your wavelength becomes much larger than water depth. So in a mathematical sense, one can write the Arcel's number as the ratio between wave height to the average water depth multiplied by the ratio between the wavelength to the water depth, the square of that. So in a simple mathematical term, I can write the wave height multiplied by the square of the wavelength divided by the cube of the water depth. So I'll say it again. So Arcel's number can be written as the wave height multiplied by the square of wavelength divided by the cube of water depth. So this is a very, very popular relation that Arcel has derived. Now this relation can be very effectively used for the long waves. So what is the definition of a long wave? The definition of a long wave is the wavelength lambda is very, very large as compared to water depth. And suppose you have got a very long wave having a small Arcel number, you can find out what is the value. The value comes nearly 32 multiplied by the square of pi divided by 3. So if you try to simplify it, it comes close to 100. So if your Arcel's number is coming close to 100, one can say that the linear wave theory is applicable. Otherwise, you cannot use the linear wave theory. That is the breaking point. So the breaking point is Arcel's number. So if your Arcel's number is within this limit, your linear wave theory is valid. Otherwise, your linear wave theory cannot be used. Now, suppose your linear wave theory cannot be used, then what else can be done? For that, there is a different type of theory which is called as the Krautberg-de Vries equation. It is also called as, very popularly called as the Bosonic equation. This equation basically has come from the classical paper of Stokes, 1847. So these are some of the popular theories that we have to understand the wave process. Now this figure actually gives an idea. If you see the top left panel, see this figure, basically the top left panel, this basically shows the waves in the deep ocean. The same waves, if you see in the shallow water, you can see how smooth it is. It looks very smooth. So what you're understanding from this figure is the amplitudes are small, the wavelength is large. And of course, because what happens is the wave gets refracted and the direction of the wave changes. You can see the wave refraction here, how the deep water waves are basically refracting, and when it is coming to shallow water, it is coming normal to the coast. And suppose the wave comes into port and harbor. In many locations, we are having port and harbor. So suppose we take a port and harbor, you are having a lot of structures. The structures can be primary breakwaters, detached breakwaters, submerged breakwaters. Then you can have secondary breakwaters, different types of structures. So when these waves interact with these structures, you are having a different type of wave pattern that is produced, that is called the wave diffraction. So wave diffraction is another important process that happens in the very shallow waters. Now the last panel of figures basically shows a different type of wave system which is not fully understood. These are called as the freak waves or rock waves. You can see a ship actually encountering a freak wave. These are very high waves. The height of these waves can be around 100 feet. You can imagine a 100-feet wave coming in front of you. So these waves are extremely dangerous, and these are also possible in the deep ocean. So the wave modeling is a subject to model these categories of waves, and you can do the prediction. The prediction can be done for about 5 days or 7 days in advance. So that is what I'm going to cover up in this talk. This is another type of course, this is similar to what I said in the previous slide. You can see the wave refraction. This is due to the wave, see these orthogonals are basically the wave rays which are coming towards the coastline. You can see that there can be convergence and also divergence of wave energy. This convergence and divergence of wave energy has a direct dependence on the bathymetry. Bathymetry means the water depth. So depending on the water depth, the refraction patterns can be different. So in some places you can have convergence of energy, and in some places you can have divergence of energy. Now this convergence and divergence of energy has a direct relation with the sediment transport. Today actually sediment transport is also a very important topic. A lot of, you can find in many of the coastlines that the sea erosion is taking place. A lot of coastlines are getting eroded. So erosion is basically sediment transport, it is a subject of sediment transport. So the waves play a very important role in sediment transport mechanism. So this slide also gives you an idea about the wave processes. You can see that these are called as the breaker zones. This is very clearly visible when you go to the beach. So the breaking of these waves, this breaking of the waves can be defined by using a number which is called as the surf similarity parameter. It is also popularly called as Ribaren number. So Ribaren number basically can tell you the type of breakers. Mathematically, you can write a simple formula for that. It can be expressed as the tan alpha. Alpha is the slope of the beach. That means the tan of alpha divided by the h by l, the square root of h by l. That means that h by l you can get from the linear wave theory. So if you know what is the alpha, that is the slope of the beach, and the relation of h by l from the small amplitude wave theory, you can find out a parameter called zeta. Zeta is basically the surf similarity parameter or the Ribaren number. So this number is extremely important to find out the type of breakers. So you can have different type of breakers. If you take the Indian coastline, the type of waves that you have in Visakhapatnam may not be the type of waves that you have in West Bengal. It may not be the same type of waves that you have in Kerala. It may not be the same that you have in Gujarat. So different coast actually has got a different type of wave characteristics, and the Ribaren number can explain how these breakers can be defined. So the wave breaking is a very, very important subject. So the separation of water particles from the wave under the action of gravity, it is called as the wave breaking.
Sorry for the interruption.
Yeah.
Sorry for the interruption. Sorry, Can you go to full screen? Yeah.
I'll go to the full screen. Yeah. Okay.
Okay. Thank you.
Yeah.
Full screen.
Yeah. It is clear now. It is clear. Is it okay now?
No problem.
Yes, sir. Go ahead.
Yeah. So you can see from this figure, you have three types of breakers. You have a spilling breaker, then I've got a plunging breaker, then I've got a surging breaker. People who have gone to different beaches must have seen this. So if you go to Visakhapatnam, you can find these type of breakers, like the plunging breakers. If you go to Balator in Odisha, you can find these type of breakers. Of course, the spilling breakers are there in few locations in India. So this basically depends on the Ribana number, just now what I was talking about. Now, there are long waves and extreme waves that you have in nature. Tidal waves are one among that. Then you have got swells. Swells are basically the long waves. Then you have got a different type of wave system called the sieges, or the residents in the open harbor. And extremely dangerous waves are called the freight waves or the road waves. Now let us see what is the difference between the wind sea and swells. So wind seas are basically the short gravity waves. So if you take the spectrum of waves from 2 seconds to 30 seconds, you can say the waves which are less than 10 seconds, or strictly speaking about 7 to 8 seconds. So these are the category of waves that you get, or called as the short period waves. So wind seas are something different from the swells. The swells are basically the long waves that generates from the generating area. Some of you must have experienced that when you go to the beach, you find that the sea is very rough, but the atmosphere is very calm. It is an indication. It is an indication that there is a cyclone which is far away. Suppose you have got a cyclone in the deep ocean. These cyclones can generate swells. The swells can travel very fast. It can reach actually the coast in about. It can reach about 1 day or less than a day, and you can find that the waves in the coastal regions are very rough. So now I'll go into the talk about the wave spectra. So the numerical modeling of ocean waves, I will be first covering about the wave spectra, the model classes, generation, and the numerical wave modeling. As I was saying earlier, the development of the spectra started somewhere in the year of 1950s. So 1951, there was a very popular spectrum that is developed called as the Phillips spectrum. This was the first spectrum that has been developed and documented. Now, if you see the formulation of the Phillips spectrum, this E of F represents the energy as a function of frequency, and you can see this is the wave frequency which is proportional to F to the power of 5. In other words, you can say that the energy is proportional to the inverse to the 5th power of frequency. This was a contribution which was made in 1951, and thereafter, but one of the problem with this Phillips spectrum is this spectrum has been developed only for the high frequency side. It does not tell what is happening in the low frequency. That is the reason why the spectrum has not become popular. But this spectrum is a foundation. It has basically it tells actually what type of energy levels that you can expect in the high frequency tail. Then in 1964, there was actually a study which has been done by Pearson and Moskowitz. And Pearson and Moskowitz actually has developed a spectrum which is for the fully developed sea. The fully developed sea. And this is what the formulation looks like. So we can express the energy as a function of frequency. Of course, this is a one-dimensional formula. This is proportional to inversely proportional to the 5th power of frequency. And this capital U is the wind speed, which is measured at a height of nearly 19.5 meters from the sea surface. So this was a contribution which was given by Pearson Moskowitz. Now what this spectrum basically explains is the energy level. It can basically give you the entire history of all types of waves that is present in a particular location. So the spectrum or the development of a spectrum forms a very, very important contribution in the subject of wave modeling. So in 1964, this spectrum was very popular. But after a period of nearly 10 years, this spectrum also had a limitation. This spectrum is for fully developed case. Fully developed means it doesn't give an idea of how the wind waves are evolving with time. Not only that, this spectrum may not find much applicability in shallow water. That is the reason why a different type of spectrum has been developed. And it was developed in the year 1973 by a group of people who has conducted the experiment in the North Atlantic. And they have come out with a formulation which is a superior formulation as compared to the PM spectrum. The importance of this particular spectrum is you can express your energy which is very much similar to the PM spectrum, but you have an extra term here called gamma F. This gamma F is called as the peak enhancement factor, which basically controls the shape of the spectrum. Now, the difference between the PM spectrum and the Jones Webb is the shape of the spectrum. And of course, it definitely makes a lot of sense, because when you have a wave system which is coming from the deep ocean to the shallow water, what is happening is the wave is getting refracted because of bottom friction. And another thing is that the universal characteristics of the directionality of the wave is lost, which basically means to say that the waves doesn't have the freedom to move in 360 degrees. Why it cannot move in 360 degrees? Because the bottom is controlling it. So the bottom is trying to control the waves so that its direction is getting limited. So when the direction becomes limited, the energy gets focused to a particular band of frequencies in that particular band of direction, or the directional band. Your frequency band is limited, your directional band is also limited. So what happens when you have that condition is the spectrum becomes more sharp. So the shape of the spectrum changes. So that is what the contribution of Jones Webb. In PM spectrum, if you try to see the shape of a PM spectrum, it looks like a Gaussian distribution. The Gaussian distribution may not hold good in shallow water. So in shallow water, the Gaussian distribution should get transformed into a Rayleigh distribution, because the Rayleigh distribution has got a sharp peak. So that is what the contribution of gamma F. So in the same equation, if I put gamma F equal to 1, then there is no difference between Jones Webb and the PM spectrum. Now, to understand the wave heights, wind and fetch. So what is happening is the energy from the wind is transferred to the waves. The waves lose the energy due to white capping. It can interact. The waves can interact with each other. The waves can break. And due to breaking, that is called the dissipation, the energy can be lost. So there are some very, very important physical formulations that has to be taken into account. Now, before I go into the next slide, I would like to give some details about some of the historical developments that has been done for the Indian coast. If you look back, the developments started in the year 1980s. In the 1980s, there were very few institutions in India which started the work on ocean waves. So some of the studies, I can highlight some of the few studies done by researchers. In 1982, there has been a study from the Naval Physical Oceanographic Laboratory, NPOL, Cochin, by Prasad Rao. He has basically developed actually a location-specific wave hindcast for the Mangalore in Karnataka coast. And Prasad Rao in 1988 actually has also developed a spectral width parameter for ocean waves. And in the next year, that is 1989, he has come out with a very important study, which is called as a time delay concept for the wave forecasting technique. So parallelly, along with NPOL, there is another institution in Trivandrum, which is called the Center for Earth Science Studies. Today it is called as the National Center for Earth Science Studies. So the group actually from NSES, like Baba and his group, actually Baba was pioneering the wave research program. They have studied actually they have made very important contributions like wave refraction to understand the wave refraction characteristics. And in 1985, there was a very important paper. It was published in a Mahasagar. It's a bulletin of the National Institute of Oceanography. So in 1985, there was a very important paper called the new trends in ocean wave research in India, published by Baba. In that is one of the starting, or you can say the fundamental work which has basically served the interest of ocean wave research. And after that, a lot of studies have been done to understand the wave diffraction model by bottom friction, like Kurian. Kurian was also in the same group of Baba from NSES. They have done a lot of studies on waves. Then thereafter, actually, NPOL, like Swain actually has carried out some very notable studies on the numerical wave prediction models. He has done a lot of case studies for the Arabian Sea and the Bay of Bengal. And the wave energy program actually was getting importance at that time. So Ravindran and Kula in 1991, they have actually published a paper on wave energy program. And Chandra Mohan from National Institute of Oceanography, Goa, they have actually compiled all the ship data and they have developed a wave statistics to understand actually the wave characteristics for the Indian seas. Then Sanil Kumar also has done a lot of studies actually like some of his notable contributions are on the directional spread of ocean waves. Then along with MC Dio, they have published a paper in 2004 they have come out with the design wave parameters using the ship data. And these are some of the contributions which has used actually the observational programs like the Ocean Boys and other sources of information in understanding the wave statistics. In parallel to this, there has been a lot of good studies that has been done using the remote sensing data also, because the satellite data started coming after the late 1980s. So today, if you see from 1990s or starting from 1991, you can get some satellite data available. So this work was initiated by Professor P.C. Pandey. Professor P.C. Pandey was from Space Application Center, Ahmedabad, and his group actually, Dr. Abhijit Sarkar, Dr. Rajkumar. So they were actually involved in the satellite remote sensing. That means they have also published a lot of studies on the role of remote sensing in coastal oceanography. So if you look into the wave research in India, there has been focused research on data collection, data analysis using in situ measurements. There has been effort which has been done on developing numerical models. There has been effort in using the remote sensing data. And today, if you see all this, you have plenty of data today from remote sensing satellites, from in situ. And so today it's a challenge actually to develop sophisticated models and improve the prediction skills. And that is what I'm going to highlight in the coming slides. So I will just skip this because this is I already mentioned this. So if you look into the first generation models, the first generation models are basically empirical models. If you see this, these are the non-dimensional parameters like for the duration limited cases and the fetch limited cases. The fetch basically talks about the area in which the wind is blowing, and duration basically refers to how long the wind was blowing. So understanding the concept of fetch and duration, there has been mathematical equations developed to make the non-dimensional wave heights and the non-dimensional duration as what we see from this equation. And the other important contribution basically was to understand the angular spreading of swells from a storm. So what happens is when you have a wind system which is generating the waves, you are having the wavelets of different wavelengths which are generated. Now, if you look into the wavelets that are generated, you can have wavelets which are having 6-meter wavelength. You can also have wavelets having 10 meters, 15 meters, 100 meters, 200 meters, going up to 1.3 kilometers. In other words, one can say that the longer waves can travel faster than the shorter waves. So the longer waves can leave the generating area and they can reach very fast. So this basically, a sketch actually shows how the angular spreading of the wave energy takes place. And this was a very important contribution which was made in the year 2004 by a person called Mitsuyasu and Honda, Japanese group. They have actually come out with a mathematical formulation coming with a cosine square formulation. The curves that we see in this figure can be conveniently expressed in mathematical form as cos square theta minus phi. Theta is the wind direction and psi is the wave direction. So this directional spread of wave energy is also very, very important. Now this has been incorporated into the state-of-art wave models. Now to understand the wave mechanisms, there are three important things which are very, very important. One is the wave growth, the one is the wave propagation, the last part is the wave dissipation. So one should understand how the wave growth takes place, how the propagation occurs, and how the dissipation finally happens. Now, before I give a small description about this sketch, I wanted to give some general idea about the wave growth, how the wave growth actually happens when the wind is blowing on the water. Now, to understand that concept, let us take a very simplified approximation. Let us take a tank of water, a tank which is filled with water, a tank having a finite dimension filled with water, and you're pumping wind on the surface of the water. That means the wind is basically blowing on the water surface. Your tank has got a finite dimension. Now let us say the dimension of the tank is 50 meters by 50 meters. So along the x direction, your dimension is 50 meters. Along the y direction, your dimension is 50 meters. You are blowing the wind speed, a constant wind on the water surface. Now let us try to observe what is going to happen with time. So what has happened is, I have taken a tank of water, the water is still and the wind is blowing on the water surface. After a period of time, I find that the surface of the water slowly becomes deformed. The deformation can be seen very clearly on the water surface, and the deformation increases with time. Now, what is the deformation and how did the deformation first come? That becomes very important. That becomes a very fundamental subject. The deformation happens because of the pressure fluctuations on the water surface. And in the year 1924, there is a very similar type of wave. If I look into the wave, you're having two sides. One is called the windward side, other one is called the leeward side. The leeward side is basically the opposite side, which is protected from the wind. So that means if I assume that the wind is blowing in one direction, the windward side is getting the energy from the wind, the other side is sheltered. Now the pressure difference between both the sides of these waves are the responsible factor for the waves to grow with time. This is what Jeffries has told in 1924. Now, let us go back to the tank which I have just now said. I have assumed that the dimension of the tank is 50 meters by 50 meters. Let us say that a 10 meter per second wind is blowing. Now, when 10 meter per second wind is blowing on the top of the tank, after a long period of time, when I do the monitoring of the wave height, I may find that the wave height is about let us say 50 centimeters. That is the maximum wave height that is possible in the tank. Now what I do is, I increase the dimension of the tank. From 50 meters, I increase the dimension to 200 meters along the x direction and 200 meters along the y direction. And the same wind is blowing on the top. Now what do I get? After some time, I'm again monitoring what is the wave height that I'm finding on the water surface. So when I do the monitoring, I may find actually the 50 centimeters or the 50 centimeters or something like that. You see, 50 centimeters is just a number which I'm talking. It can be anything. Now what I find is the wave height has increased when the dimension of the tank has increased. So if I keep on increasing the dimension, now the 200 meters I made as 500 meters. Now what I find, if I made it as 500 meters, the wave height has further increased for the same wind speed. If I keep on increasing the dimension, there is a cutoff value, which basically means for the given wind speed, there is a particular optimum dimension of the tank which can give you the maximum wave height. So that is what we are defining as a fetch on the water surface actually, the area over which the wind is blowing on the water surface. Now why did I take the tank experiment? Tank experiment is the most simplified experiment that one can think about. The ocean is an infinite tank. Its dimension is very large. So you can have different type of fetches on the water surface, and the different fetches can create different type of wave heights. The wave directions can be different. The wave can propagate in multiple directions. The energy propagation can be it can be non-linear. So the real ocean surface, if you're looking into the ocean surface on a macro scale, what we find is the waves generated from one point can reach some other point in no time, and it can modify the waves in that region. So it is a very, very complicated process. We cannot describe the ocean processes or the ocean waves in a simple tank. It is not possible. The tank is just a simple for understanding I have given the concept. Now, yes, this figure is a very, very important thing. After Jeffries has given his theory in 1924, 1951, there has been a lot of interest which has been generated in the people to understand actually how the waves grow with time. Suppose, of course, the wind is generating the waves, but how does the wave grow with time? Whether it is linear, whether it is exponential, or what type of function is valid. Now, there has been a lot of debates on this, and there was a very outstanding contribution made by O.M. Phillips. O.M. Phillips is a very well-known fluid mechanics. So in 1951, what O.M. Phillips said was the growth of waves should be linear. And he proposed actually that the growth of waves has to be linear. But when Phillips has proposed this theory, there was a student called Miles. Miles was a student working with Phillips. So Miles was also conducting the similar experiment, but Miles has come out with a different type of results. And Miles was puzzled actually, whether Phillips was correct or whether he was correct. But what Miles mentioned was, the growth will not be linear, it has to be exponential. It is contradicting what Phillips has said. Now there was a long debate actually, who is correct, whether Phillips is correct or whether Miles is correct. After a long debate and after many long years, it was felt actually that both were correct and both were wrong. Now the point is, when are they correct and when are they wrong? That becomes the point. So Phillips is also correct, Miles is also correct. Now let me tell you when Phillips is correct and when Miles is correct. So if you take the tank experiment, which I just now mentioned, so what is the assumption that we have done in the tank? The water surface is still. Still means there is no waves. The wind is creating the waves. If we have a similar phenomena in the ocean, that means when the ocean surface is flat, no waves, and when the wind is blowing on that area, then Phillips said was correct. The growth of waves will be linear. But suppose already you are having an existing wave, on top of that wind is blowing, then what Miles has said is correct. So in the real nature, linear theory is also valid, exponential theory is also valid, both are valid. So linear theory is valid under a particular condition. Miles theory is valid when you are having an existing field. So that is what you see in this figure. So this figure actually was been taken from Barnett and Wilkerson. Barnett and Wilkerson, they have actually studied this linear growth theory and the exponential growth theory, what Phillips and Miles have told. And this curve basically shows the linear growth, then you have got the exponential growth. After some time, what you're having is, you're having overshoot and undershoot. You can see that. So this is again an idealistic case. Why it is idealistic case? Because here I am assuming that the wind is constant. Suppose if I take a 10 meter per second wind blowing on the water surface, what the 10 meter per second wind is basically doing, it will create waves. And on the top of the waves, again the wind is blowing. Then what the wind is doing, it is cutting away the top of the wave. It's called wave breaking. So you are having wave growth followed by wave dissipation. The dissipation occurs when the waves have become saturated. When the energy of the waves have become saturated, the waves further cannot grow. Then what will happen? It gets dissipated. So when dissipation happens, what happens? The energy goes down. When the energy goes down, the wind is again pumping energy. Again it grows. Again the wind will break the waves. Again the energy goes down. So that is what Barnett and Wilkerson in 1967 has said. What he said, when the waves has reached a saturation limit, it will be an oscillatory nature, as what we see here. You can find a overshoot followed by undershoot, again overshoot followed by undershoot. Now from that condition, if the wind speed increases, then again you will have an exponential growth, and then again there can be overshoot, undershoot. So this is the basic foundation that has been some of the very popular studies that has been done on the subject of wave modeling. Now, as I said earlier, you are having the first generation models, second generation models, and third generation models. I already talked about the PNG and SMB nomograms. PNG stands for the Pearson, Newman, James. SMB stands for Swedrup, Monk, and Bretzneser. So these are basically nomograms. In the coming slides, I'm going to show you how a nomogram look like. Then after that, you had the second generation models. You have so many classes called the coupled hybrid, discrete parametric, then coupled discrete. Of course, there is a spelling mistake. It should be CD. It should be coupled discrete, etc. There are so many categories in that. And in third generation models, we have the WAM model that is developed by the Max Planck Institute from Germany. Then you have got the WAVOS 3, WW3. It stands for WAVOS 3, developed by the NOVA, USA. And you have another category of model called SWAN, simulating waves near shore, developed by Netherlands. Now this is how a nomogram looks like. The PNG, they say the Bretzneser's nomogram. If you look into this figure, you can see that the x-axis, the y-axis is representing the wind speed. You can see the wind speed is changing from 0.1 going up to 30 meters per second. And the x-axis of the figure is the duration, how long the wind was blowing. See, this is up to 96 hours. And you can find so many curves on this particular figure. You can see this. And on each of this curve, you're having some numbers you have marked. 0.61, 1.5, 2, 3, like this. This is basically the fetch. The fetch is a distance over which the wind is blowing. If you have these three primary information, you can pick out and tell what is the wave height. So you can find out from this what is the wave height and what is the wave period. This is how the nomograms has been used in the earlier days. Now this nomogram is also having a limitation. Now let me tell you what is the limitation. This nomogram is the backbone of this nomogram is a semi-empirical relation. This semi-empirical relation is a non-dimensional parameter. Now the non-dimensional parameter connects fetch, wave height, and the wind speed, and also the wind duration. Now this mathematical formulations does not have any physics in it. It's only a non-dimensional parameter. Now where does this nomogram fail was, let me give an example. If suppose a 10 meter per second wind is blowing on the water surface for a long period of time, then if you're doing the same experiment in two different locations, you should have the same wave height. the same wave height, which basically means if I do an experiment, one in India, another experiment in the Europe, having the same identical conditions, then I should have the same wave height. But that is what the nomograms say. But when you look in the real field, they don't match. That means if I'm getting a wave height of 1 meter here, in Europe I may be getting 1.5 meters, which basically means to say the validity of the nomogram is questionable. That is where it failed. The universal validity of the nomogram is not valid because it doesn't have any strong physics. Now let me come into the energy balance equation. This is how the energy balance equation looks like. So as we see the left hand side of this equation, it's a differential equation in which you are taking the time variation of wave energy added with the spatial variation. This is a Laplace operator. It can be expanded as del by del x plus del by del y. This is a dot product. Cg basically represents the group velocity of the waves, and E is the energy, which is a function of frequency, direction, position, and time. Now this is the terms that you have on the left hand side. On the right hand side, you are having 4 distinct terms. SIN basically stands for the input of energy from the wind. SNL basically stands for the nonlinear wave to wave energy transfer. SDS basically represents the dissipation of wave energy due to wave breaking effects. And when the waves comes to the shallow water, you're having bottom. That means how the bottom basically plays a role in what you can say in redistributing the energy. So the combination of all these terms, these are basically the physical parameterizations that you had in the second generation and also in the third generation models. And improvement of these terms is a very active area of research. So the young researchers actually should think about how we can come out with a better formula. So today we are already having formula, but there are scope of improvement. We have to see how better we can come out with better formulations so that you can add new knowledge actually to the subject. Now this is how a figure looks like. So this figure basically shows you the significant wave height for the Indian region. This figure is basically produced using the WAM model for the Indian region. As you see from the figure, these are the different months. During the month of April, this is how your wave height looks like, you can see. And if you come to July, you can see in the month of April along the Arabian Sea and the Bay of Bengal, you can see the wave heights are about half a meter or less than half a meter. But when you come in the month of July, which is a strong southwest monsoon period, you can see the regions of Somalia, the wave heights can go up to 5 meters. 5 meters. So this type of information, so this figure basically gives you an idea, the output of the wave model. So this is the wave height and wave direction. Similarly, you can get the wave period, you can get the wave spectrum, you can get the information about the significant wave height for the swells, you can get the swell wave period, the swell wave direction. So all these parameters you can get using the numerical wave models. So the basic equation of a numerical wave model looks the same. This already I have mentioned in my previous slide. So you need to have the balances between these terms. The balances between all these terms as what we see in the right hand side. Now, the spectrum, if I take a standard spectrum like a Gaussian distribution or a normal distribution, the shape of that looks like a bell. So this is how the spectrum looks like. The red color basically shows the wind actually. The wind is basically giving the energy distribution like this. Now when the wind is generating the waves, what is happening? Wavelets are generated. When the wavelets are generated, you are having different type of individual waves which are created, and these individual waves move with a different speed. So when they move with a different speed, they interact with each other, and during the course of interaction, there will be a nonlinear wave-to-wave interaction which can redistribute the energy within the wave spectrum. So you may have a nonlinear interaction between wavelets, and this nonlinear wavelet is the pink color that we see here. So on the high frequency side, what is happening is the nonlinear wave interaction is contributing to the energy development. But when you come to the higher frequency side, what happens is, of course, when you are coming towards the higher frequency side, the nonlinear wave interaction is trying to take away the energy from the wave spectrum. And when you come to extremely low frequency side, it is again adding the energy. So this is the role of nonlinear wave-to-wave interaction. Now, when I come into the shallow waters, then you are having a bottom interaction, then you have got the wave breaking. So both of these are again what you can say dissipative mechanisms. If I take the cumulative effect of all these processes that you see in this figure, you get total energy of the wave system. So the total energy of the wave system, if I integrate for all the frequencies, of course it is integrated for all the frequencies, you get the total energy, and from the total energy what I can get is I can get the significant wave height. the highest of the 1/3 waves in the record, I can get what is the wave period, I can get what is the wave direction. Now, of course, these are some general things about the third generation wave models. The original wave model was developed by Coman et al. Coman was a person actually who has contributed a lot. It has taken nearly 7 years to develop this wave model, and the spectral resolution and the spatial resolutions are flexible, and the model can be run on the global scale. It can also be run on the regional scale. Now today, if you see, these third generation models are run on a global scale. There are some websites actually from where you can get this data. If you can go to NSEP website, you can find the global forecast. If you go to ECMWF, the European Center for Medium Range with the forecast, you can get the global wave forecast. So this wave information is dynamically updated with time, and this is coming from a third generation wave model. You have a different type of wave model called the WaveWatch 3. This is a wave model which is parallelly developed by a person called Tolman from USA. And it uses the same energy balance equation, but there are differences in the physical parameterization. So that is some of the differences that you find between the WAM model and the WaveWatch 3. Now you have another type of wave model which is developed by the civil engineering department of the Delft University, Netherlands. It is called the SWAN model. It stands for simulating wave near shore. It is a state-of-art wave model. Today, actually, this model is being widely used by the scientific community. Even the coastal engineers basically uses this model because the model is proven to be very good. And in addition to this, you are also having commercial models like the Mike. The DHA has developed their own wave models called the Mike models. But of course, that is a commercial model. It's something like a black box. You cannot do anything actually. If you want to change something else, you cannot do. So these are all open source models which I am just now explaining. So for the research perspective, actually you can do many things with this model. And the SWAN is basically a robust model. If you see SWAN, there are so many functionalities as what you see in this slide. You can actually estimate what is the wave induced setup. You can actually also find out what is the transmission through obstacles. You can study diffraction. Many processes can be understood. So for any wave model, there are basically two important quantities which are important. One is bathymetry. Bathymetry means the water depth. So how do we get this bathymetry? For a very large area. For a very large area, it is very difficult to do survey everywhere. Survey has been done in so many locations, but survey has not been done at all the points. So if you go to the National Geophysical Data Center, NGDC, there's a website, you can search it in the net. If you click on NGDC, you can go to the global ocean relief bathymetry. So once you go to if you go to that link, there is a freely available data for download. It is called eTopo 1, eTopo 2. That's the topography. You can get the entire topography of the world, including the oceans. So if you take eTopo 1, so the 1 basically represents 1/60th of a degree. 2 represents 2/60th of a degree. So the highest resolution what we have today is called GEPCO, GEBCO. You can download this data, which is also freely available. So from the GEPCO data, you can download the bathymetry, and the resolution of the GEPCO is 30 arc second. 30 arc second means approximately it comes to around 900 meters. That is the resolution that you have for the global topography. So the bathymetry information you can use either eTopo 1, you can use GEPCO. It's up to your choice. Now for the surface wind field, we can get it using the atmospheric models. So these are the two basic information required if you want to run a wave model. Without this, you cannot use a wave model. So you require the wind information, which basically means the wind speed and wind direction, which you can get using the U component and the V component. When you download a data from the atmospheric model, the data is available in the form of U component and the V component. If you know the U and V component, you can find out what is the speed and direction. It is very simple. You take the square root of U square plus V square, you get the magnitude, and the tan inverse V by U gives you direction. Of course, you have to do the quadrant correction. So like this, you can actually get the information about the bathymetry and the wind field, and the output from the wave models can be one-dimensional spectra, it can be two-dimensional spectra. You can get the information about the significant wave height, wave period, and wave direction. So many parameters. So I will not go into more detail because this is available in the net actually. So I will skip this information. And the SWAN model can be run in both stationary mode and non-stationary mode. Of course, for a beginner, actually, you can use the model in stationary mode. Stationary mode, basically, you can assume that the wind speed is constant, and you will be getting actually the maximum possible wave height that is possible in the particular region. Non-stationary means your wind field is dynamically changing with time. So you can use the SWAN in both the options. Now, if you look into the formulation that you have in the SWAN model, you can the formulation is basically the SIN is the input term. This is the intrinsic frequency, and this is the direction. So you can write this as a sum of A. A basically stands for the linear growth. In the previous the presentation, I was mentioning about the Phillips linear growth. This A represents that linear growth. So you have a combination of linear growth and exponential growth. So A represents the linear growth, and this B represents the exponential growth. So this is a function of wave energy again. And of course, if I go into more details, there is a coupling coefficient actually between the atmosphere and the ocean. I'm not going into details of that, but because of lack of time. But this is how the formulation basically looks like in the SWAN model. Now, the distribution of wave energy can be expressed as a functional dependence of a steepness dependent parameter. So basically, this parameter is used actually by a formulation given by Komen. It basically closes your energy balance under a given set of conditions. And you have another formulation which is given for the bottom friction. So this is a coefficient that you see. This coefficient suppose if you look at the ocean bed, some of the places you're having the sandy bottoms, in some places you've got mud, actually some places you've got rocky bottoms. So depending on the type of, depending on the heterogeneity of the bottom, you can define the appropriate parameterization, and you can use this. And finally, you can find out what is the depth induced breaking and all using these particular formulations. I will not go into more details, but if somebody wants to know, I'll be very happy to discuss more about this. Another term, which is called as a nonlinear wave-to-wave interaction. This nonlinear interaction is one of the most complicated process that is very, very difficult to understand. But in a nutshell, I'll try to tell how this theory has been used. It basically comes, the concept basically comes from the Brownian motion in physics. I think all of you may be aware about the Brownian motion, the motion of actually particles in a closed jar actually. Now these particles which is moving, move randomly and they weakly non-linearly interact. So the similar concept has been used in the nonlinear wave-to-wave interaction theory. And in context to ocean waves, there is a very popular theory which has been proposed in 1985 by a person called Hesselman. And the theory that he has proposed is called as a discrete interaction approximation theory, which talks about the nonlinear interaction among 4 different wave numbers in orthogonal directions. The balance of this energy is what you see in this equation. And of course, this equation has been revisited and also modified in 1996 by a person called Elberke, who said that there is no requirement of taking all the 4 wave numbers. You can reduce the 4 into 3. So he came out with a different theory called as that lumped triad approximation theory. The lumped triad approximation theory, which is validated in shallow water. So this is how the equation basically looks like. And this equation basically is a combination of wave numbers, K1 and K2. Now what we need to do here is, we need to take the permutations and combinations of all the wave numbers that can exist at a particular given point. And this is the parameter which consumes the maximum computational time when you're running a wave model. So there are a lot of scope of improving this, because I think there is a lot of research which is going on. How can we optimize this particular term? Optimization of this nonlinear interaction. The reason behind it is you cannot find out the exact solution. It's not possible. But you can optimize it to come out with a solution which is valid. Now this is how the nonlinear interaction basically looks like. You can see the curve here. It is very nonlinear. It is basically frequency dependent. The nature of the curve is dual nature. On the high frequency side, you are having a positive lobe, and the lobe actually becomes negative when you come to the lower frequency. And of course, there is a lot of debate on this also, how the transfer of energy takes place and how it affects the peak frequency. Now I have just actually covered some important aspects of the wave modeling. Basic equations, what are the models that are available for understanding the ocean waves? There has been a debate, I think about 15 years back. What are the next things that we can do to improve the wave models? Now the question is, since it's a differential equation, you do not have an analytical solution for this equation. So you have to go for numerical techniques. There are higher order numerical techniques which can be used to solve the equation. So when you use a numerical technique, the numerical technique is not exact because you have got the truncation errors and the errors propagate with time. So there is a debate whether improving the numerical technique can improve your efficiency. The answer is it is not much. The improvement in the result is minor, but the results can drastically improve your physical formulations. The physical formulations is the second part. The physical formulation is what I have shown in that equation. If you're able to come out with a better and sophisticated equation which can describe the processes, the physical processes properly, then you can do, it's a very important contribution that you can do in this field. And another important thing is the quality of the wind. The wind is extremely important. Now let me give you a very simple idea why the wind is important. Because the waves are created by the wind. Suppose there is an error of 10% in the wind. Error of 10% in the wind. This 10% of error can lead to 20% of error in the waves. So now we can understand how important the wind is, the quality of the wind. So the atmospheric model should be in a position to give very good quality winds. The waves primarily depends on the quality of the wind. So the example which I just now said, 10% of error in the wind can lead to 20% of error in the waves. It's a very valid statement. It's a thumb rule formula, but it is a good formula. So there are two important things that we have to look into. One is improving the quality of the wind, first one. The second thing is improving the physical parameterizations. So these are some of the things I think we should focus in the next 20, 30 years from today. There are many things which can be done. It's a very, very interesting and fascinating subject. And it is a very complex subject. That is why it is fascinating. So the researchers actually can think about how you can address this problem. It's a very complex problem having wide socio-economic impact. Now, let me come to the last part of my presentation because I think, it's only 5 minutes left, but I'll try to cover it up. The role of satellites in ocean wave research. Now, as I said earlier, the initial studies on ocean waves started with instruments, measurement, like ocean buoys were used. The buoy is a single point observation. There is no doubt actually the information that you're getting from an instrument is very, really good because that is the ground truth. But the problem with the instrument is you cannot have instruments everywhere in the ocean, not possible. Then what do you do? If you want to understand the climate and other type of things, you require a very large scale study. So for such studies, the satellites have played a very, very important and crucial role. And today it is everybody knows satellites, because the satellite coverage, it has got a global coverage, and you can have actually the data of multiple parameters over the global oceans. But the data, availability of data basically is from the early 1990s. So from 1990s till today, you're having the data. And another important thing with the satellite I just wanted to tell is, if you look into the developments that have taken place in the sensors, the improvement of sensors have actually taken place with time. So when I use a satellite data of 1990s, and if I compare with the data that we have today, one should be extremely careful because the precision was different. The bias correction has to be done. If you do not do the bias correction, your results will be completely erroneous and you may get some wrong results. So bias correction of the satellite is extremely important. I know that if you do not do this bias correction, because if you download the data and do the analysis, you may get your results may lead somewhere else. It may not be correct. So if you're using multiple satellites, you have to be extremely careful that it's a standardized data and it is data quality controlled. The quality control means you have to do actually the bias correction. And of course, there has been several studies which have been done on the bias correction. You can find in the literature. So I would like to show some results actually which have been done using the bias corrected standardized data. So these are some of the studies that has been done on the global scale. And what we have done is we have used about 21 years of data from 8 different satellite missions. And we have actually analyzed for the entire Indian Ocean region. And you can see why the Indian Ocean region is very important. Because when you look into the Southern Ocean, if anything happening in this region, we are finding actually recently that there has been a lot of activity that is happening in this region, and this activity can influence the entire Indian Ocean region. That means the North Indian Ocean can be influenced by the remote forcing effect that is coming from the Southern Ocean. And what we have done is we have done a study to understand how the waves are basically changing in the last 2 decades. This homolog diagram basically is the data that you have extracted from the satellite. So it's very clear from this figure. If you look from 1990 to 2012, all along the longitude, you can see that the wave activity has completely increased. The wind speed has increased as well as the wave activity. So this is a message which I'm trying to give from this figure. The wind speed, the maximum surface wind speed, the maximum wave height, both has increased over the Indian Ocean region. But when I look into the sector-wise, from the Southern Ocean to the North Indian Ocean, this is how the trend line basically looks like. The highest variability is found at about 50 degrees south. And when you're coming close to the equator, so this is how the equator looks like. You see this is the equator. There is no much variation that you find in the equator. But once you cross the equator and come to the North Indian Ocean, you can find that there is a slight increase in the trend line, which basically means to say that the wave heights are actually increasing. And this increase is intrinsically connected with the synoptic scale disturbances and the frequency of synoptic storms that you're having in the Southern Ocean. Now, when you take the probability density function of the wave heights, you can find a very interesting thing that is happening. What is happening is, in a nutshell, I'll try to condense this information in a nutshell. What you see from this figure? What you see from this figure is, if I try to categorize the wave heights, suppose you have got a wave height starting from 1 meter going up to 5 meters. Let us say 1 meter is your minimum wave height and 5 meters is your maximum wave height. Then what do? I categorize this from 1 to 2 meters, 2 to 3 meters, 3 to 4 meters, and 4 to 5 meters. So I'm having different categories of wave height. Now, if I look very closely into how this trend distribution of these wave heights are changing, a very interesting thing that is seen is the lower wave heights are becoming into bigger wave heights. That means the 2 meter wave heights, the frequency of 2 meter wave heights are increasing to 2.5 meters today, which basically means the extreme wave heights are increasing in the Indian Ocean. Now, what happens when the extreme wave heights increase? The direct impact is on the coastal region. The people living in the coastal regions can face the high wave alerts coming all the time. So that is the message which I wanted to give. Now, there has been recent study which has been done to understand the sector-wise distribution of the wave heights. As what you see, we have actually divided the entire Indian Ocean into 6 sectors based on the categories of waves. So these are the satellites that has been used for this particular study. We have used all possible satellites, basically starting from 1992, going up to the Southern Arctica, the latest satellites. And then we have actually tried to fix what is the threshold wind speed and the significant wave height for different percentiles, starting from 90 percentile going up to 95th percentile. And this is the long-term distribution of the surface wind speed and the wind speed, as what you can see from the figure over here, is the bias basically between the scatterometer and the altimeter for a longer time record. Now, the very interesting thing which I would like to tell from this figure is, earlier I was mentioning about fetch. Fetch is basically the area in which the wind is blowing. And today what you find is, when you look into the climate, the wave climate, the 6 regions what I have defined in the earlier figure, the variability, you can very clearly see that some of the areas, the shrinkage in the fetch, which basically means to say that the area where the wind was dominant in the last decade was not the case what you find today. Today, the fetch is also changing. That means the area of the high wind speed or the occurrence of the high wind speeds are changing with time. So we have done a trend analysis for all the 6 regions, and you can very clearly see how the trends are basically changing over all the 6 regions in the Indian Ocean region. And finally, I would like to conclude, these are the last slide actually, some of the challenges to the young researchers. It is a very high time that we should contribute, because today you are having a lot of data, you are having a lot of what you can say information available. We need to think actually how we can take this particular field in the next level. So there is a very large scope actually to improve or to develop better air-sea interaction parameterization. Today, if you see, the cyclones are increasing. I think all of you have seen that the cyclones, the very high intensity cyclones are coming in the Bay of Bengal. And also cyclones are becoming very active in the Arabian Sea. Now what is going to happen is, we need to model the cyclonic wind fields, and also the wind field that you're modeling for the cyclone has to go to the wave model. The problem is, the parameterization that we are using today has got a limitation for extremely high wind speed. So we need to see how we can develop a better air-sea interaction parameterization for cyclonic wind speed, which can be used in the wave models. We also need to see how we can develop better parameterization for the heterogeneity in the bottoms. Heterogeneity in the bottoms means, suppose you have a sandy bottom, your wave dissipation is different. If you have got a muddy bottom, it is different. But today, if you see the wave model, the parameterization is only for sandy bottom. You have to make it more sophisticated. So this is one of the challenges that is in front of us. There are different type of things like this. The other thing is that you can also include river tides and waves and currents. I'll give you a very, very important thing. When you have a cyclone which is hitting on the coastal region, you're having the storm surge. Now what happens when the storm surge comes to a place where the river is there? The storm surge can penetrate inside the river. It can travel tens of kilometers. For example, if you take the Hooghly River in West Bengal, it can go nearly up to 70 kilometers. Now, when you have a storm surge which is going or propagating inside the river, the danger is basically you will have actually the water level flooding the bank of the river. Nobody has really looked into it. It is one of the very important thing because it has got a lot of socio-economic implications. So these are some of the challenges that is lying in front of us. Then we need to also come out with better parameterization for wave tide mangrove interaction. We also need to actually come out how we can give better alerts for the high waves that are coming, like the rogue waves and freak waves, because these waves are actually there in the deep ocean. We do not have a forecasting mechanism for this. This can be very important for the shipping companies and the coastal regions. So thank you very much for the presentation, and thank you very much. So I complete my presentation.
What an excellent presentation, sir. So congratulations and thank you for your fabulous presentation, sir. So we'll go for a quick session of the questions and answers. Okay, you just go to the chat box.
Yeah.
Students from Mahendra. Sir, give idea regarding freak waves at open ocean, how it forms, how does we identify them and mechanism.
Okay. So the Mahendra, the freak waves basically were there even in the earlier days, but the only thing is it has gone unnoticed. We were not aware that such type of waves are there in the ocean. When from the satellite data, you can actually see that these freak waves are actually existing. In a day, you are having about 9 such freak waves which are existing in the global oceans. 9 such freak waves. Now these freak waves happens in those areas where you have got a very strong interaction between waves and currents. A very strong interaction between waves and currents. Now one of the region is if you take the Indian Ocean region, we are having South Africa where you have got the Agulhas current. When you take the South Africa, we are having a very strong current system called Agulhas. So when this Agulhas current interact with the swells coming from the Southern Ocean, under a particular combination, your wave heights actually gets amplified. And this amplification can happen and the heights can reach up to 100 feet. So this is one of the mechanisms. A nonlinear interaction between waves and currents can lead to freak waves. But still, there is a lot of research which is required because we need to understand